All right, so 4.3, connecting f prime and f double prime with f. So part A. Today, students will be able to determine intervals on which a function is increasing or decreasing, which is actually review from pre-calculus, and then apply the first derivative test to find relative extrema of a function. It's really a lot easier than it sounds because I've kind of already taught it to you. We're using sign charts. It's the same process, only now it's officially called the first derivative test. Example 1. Use a graph to estimate the open intervals on which the function is increasing or decreasing. So we're going to do it graphically because we have a graph available. Then find the open intervals analytically. So I'm going to show it to you. I'm going to show you how to do it algebraically or with actual math. Okay, so this function here is like an upside down, well, it's not like, it is an upside down parabola. The domain of this function, which means all the possible x values, are from negative infinity all the way to positive infinity. Right? These are the x values. So I need you to be able to tell me that this function is increasing from negative infinity all the way to right here, its peak. So along all of this, this function is increasing. So you're going to write increasing. Now the instruction says open intervals, so I'm just going to use open intervals. Increasing from negative infinity to negative 1. And then I need you to be able to also tell me that this function is decreasing from the same negative 1, but on the right side. So you see this function is coming down. So it is decreasing. So I need you to be able to tell me that as well. So it is decreasing from negative 1 all the way to positive infinity. Okay, so that's graphically looking at the graph. Obviously, this peak here is a maximum. So what we're going to do is we're going to use mins and maxes to determine where a function is increasing and decreasing. And that's going to involve a sign chart, which is only supposed to be used as a tool, not any kind of explanation or any sort of thing like that. But it is easier to do that way. So analytically, algebraically, you're going to do this just like you did 4.1, I believe. You take the function y, I'm going to write it again over here, and you derive it. So I get negative 2 x plus 1 times the derivative of x plus 1, which is 1. So there's my derivative. And then I take the derivative. Well, you know what? Let me distribute the negative 2. I take my derivative and I set it equal to 0. And then I find the critical values, the critical numbers, my critical points, or at least the x coordinate. So let's see. Add 2, I get negative 2x equals positive 2. Divide by 2, divide by 2. I get x equals negative 1. So this here is my critical value, critical number. The x coordinate of my critical point. So now I use that along with the sign chart. Okay, so here's my number line. X is negative 1. So then I have to find test values. Values on either side of this number negative 1. If I had more than one answer, then I'd find test values on either side of each critical number. But this is nice and simple. So I need to find a number to the left of negative 1, which obviously negative 2 is the next best thing, right? A small number. And I need to find a number to the right of negative 1, which hopefully 0 is your pick. Because it's 0 and it's so easy. So these are my two test values. And now what I do is I take my test values and I plug them into my derivative. Right? I'm reviewing this because I've already shown you this once before. Okay, so I take my derivative, plug in negative 2, and then I take my derivative, plug in 0, and I need numbers out of here. So apparently when I plug in -2, I get +2. And when I plug in 0, I get -2. So I'm not concerned with the number. What I'm concerned with is the sign. A +2, it's positive, and -2 is negative. That's what I'm concerned with. I'm concerned with the sign. So I go to my sign chart, and for -2, when I plugged it in, I got a positive. So for this interval, for everything to the left of -1, this function is plus, and plus converts to increasing. And then for everything to the right of -1, because when I plugged in 0, I got a -2, everything to the right is going to be negative or decreasing. So here's my sign chart. And I can determine using my sign chart that, oh, from -1 this way, right, which would be -infinity to -1, we're increasing. And then from -1 this way, which would be from -1 to +infinity, we're decreasing because it's negative. Another way to look at this, if I erase that real quick. Another way to look at this would be to interpret the pluses and the minuses as going up and coming down. So the plus could be like this, I'm going up, and the minus can be like that. Okay? And in the future, this is going to help us determine, or not in the future, I think the next example, or no, next, okay, 2 more. This is going to help us determine, oh, this is a peak. So this right here is a maximum, right? Right. So we did this graphically and analytically. All right. Example 2. Find the open intervals on which f of x equals x cubed minus 3 halves x squared is increasing or decreasing. So same idea. We're just going to do this strictly analytically using algebra and stuff, right? So derive. I get 3x squared minus 3x. So I take my derivative and I set it equal to 0. And my job here is to find when does x equal 0. So I see that they have common factors, a common factor of 3x, or greatest common factor. So when I pull out a 3x from the 3x squared, I'm left with just an x. And when I pull out the 3x from the 3x, I'm left with just a 1. So now the zero product property, 3x equals 0, so x equals 0. And then x minus 1 equals 0, so x equals 1. And here are my critical values, my critical numbers. So now I'm going to make a sign. Okay, so my sign chart, let's see, I'm going to use 0 and 1. These are my actual critical values. So 0 and 1. And now I need test values to the left and to the right of each number. So to the left of 0, -1, I hope is the most obvious choice. To the right of 1, 2. And then in between 0 and 1, I would just go with 1/2 or 0.5, however you want to look at it. So those are my 3 test values. I'm going to use those numbers and I'm going to plug them in to the derivative, right? Because this is the first derivative test. This is what I'm doing. It's the first derivative test, so it only makes sense to put those numbers into the first derivative. All right, so let's see. When I plug in to my first derivative, let's see, -1, I get +6. Then I plug in the 1/2 or the 0.5, I get -3/2. And when I plug in the 2, I get +6. So once again, remember, I'm really just concerned with the signs. This is a plus, this is a minus, this is a plus. So for -1, that's a plus. For the 1/2, it's a minus. And for the 2, it's also a plus. So now using my sign chart, I should be able to tell you, okay, it's increasing from, and remember, this is -infinity, and this is +infinity. So this function is increasing from -infinity to 0. So it's going up, right? And then from 0, let me write increasing, or inc. From 0 to 1, it is decreasing. And then from 1 to positive infinity, it's increasing. Okay? And you would have to actually write that. Once again, it says open interval, so we're just going to write in open interval notation. So let's start off with increasing. And negative infinity all the way to the 0. And then also at 1 all the way to positive infinity. And then decreasing from 0 to 1. Okay, so I haven't officially shown you the first derivative test definition, but this is basically the idea of using the first derivative to help me to analyze the original function f. Okay. Okay, so here it goes. The first derivative test. Let c be a critical number of a function f that is continuous on an open interval I, they're just calling the interval I, containing c. If f is differentiable on the interval, except possibly at c, then f of c can be classified as follows. Remember, critical numbers are allowed to be a location where the derivative equals 0 or it does not exist. It could not exist there, but the function is still going to be increasing and decreasing to either side. All right, so now the classification, number 1, if f prime changes from negative to positive. So number 1 is right here. This is an example of number 1. If it changes from negative to positive, then f has a relative minimum. So this right here is a minimum. And that's how we're going to use the first derivative test. It changes from positive to negative to positive, it's a minimum. Now notice how they write that, the notation, right here. F prime of x is less than 0 because all numbers less than 0 are negative. So if it's decreasing, the derivative is going to be negative. And then the notation for the other, when it's increasing, the derivative is going to be greater than 0, and numbers greater than 0 are positive. Right. Number 2, if f prime of x changes from positive to negative at c. So on the left it'll be positive of c, right? On the left of c, and on the right of c it'll be negative. Then f has a relative maximum. So this here would be considered the maximum. Again, notice the notation. On the left side it's positive, so f prime is bigger or greater than 0, because numbers bigger than 0 are positive. And on the right side it's negative, it's decreasing. F prime is less than 0. So this was for part 2. And then the pictures on the bottom, both pictures relate to 3. So number 3, if f prime is positive on both sides of c or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. So here, for both of these examples, it is possible for the function just to be strictly increasing or strictly decreasing and not have a change from increase to decrease or decrease to increase. At which point, if that happens, obviously there is no minimum or relative minimum, relative maximum. Okay, remember relative is local. It's like the nearby ones, not the most max or the most min, just the ones that were local. Because for these pictures here, if let's say these were the closed intervals, then at A, for this first picture, this would be the minimum, the absolute minimum. And at B, this would be the absolute maximum. Relative, remember, is in between well, not necessarily in between, but yes, not the most of anything. Okay. Example 3, find the relative extrema of f of x. So now we're doing the relative extrema. That means you need to tell me where are the mins and where are the maxes. And we're going to do this analytically, kind of, because we're going to derive, but we're not going to set it equal to 0. We're going to analyze this function's equation. All right, so derivative first. So f prime of x equals, okay, bring the 2/3 to the front. This is a chain rule, so the inside function stays exactly the same. I subtract 1 from 2/3, so I get negative 1/3. And then I have to multiply by the derivative of the inside, which is 2x. So if I clean this up a little, I get 4x over 3. And then I can write this correctly. It'd be the cubed root of x squared minus 4. And then that's over 1. And again, if I can write this again prettier. 3. Oh, hold on. I wrote those too close together. 3 cubed root of x squared minus 4 over 4x. Alright, so I'm going to write some stuff down. Hold on a second. Alright, so we're going to analyze this function because this is not pretty. This is not something we want to set equal to 0 and figure out what the what the critical values are. Oh my goodness. Okay, so it's just easier to do it this way. It's a rational function, which means it's a fraction basically. So it's okay. So analyze the function. So if I look at this function and I look at the top, 4x, I know, and you should know, that whenever the numerator equals 0, the entire thing is going to equal 0, right? So isn't that what we do? We set the derivative equal to 0. So if I have 4x equals 0, right, then x is going to be 0. So when x equals 0, right, my derivative equals 0. So this is going to be a critical value. Now if I look at the bottom, it's a fraction. The bottom, the denominator, cannot be 0. Right? That's a problem. So the derivative is not going to exist if the denominator equals 0. So we need to figure out, okay, what numbers could we plug into the bottom, the denominator, in order to make it equal 0? And then, so hopefully you're thinking, okay, what number squared minus 4 would give me 0? Oh yeah, 2 squared. And it's actually going to be plus or minus 2. Okay? If I plug either one of these two numbers into the denominator, my denominator is going to equal 0. And you know that's no bueno. So my derivative at x plus or minus 2 does not exist. Okay? So those are the locations where critical values occur. They happen when the derivative is equal to 0 or it does not exist. So these three numbers, 0, -2, and +2, they're my critical values, and I'll use them to do a sign chart. All right, so I drew out my sign chart up there. I need to pick test values to the left and to the right of each one of these. So -3, -1, +1, +3. And of course, I'm going to skip the whole plugging in because you should be able to do that. So when I do plug in my -3, I do actually get a negative number. So for that interval, to the left of -2, this function is decreasing. When I plug in -1, I get a positive. When I plug in +1, I get a negative. And when I plug in this +3, I get a positive. All right, so now these pluses and minuses, they're going to help me determine if I have a max or if I have a min. Now, if you want to go back to the definition of first derivative test, if at C it changes from negative to positive, such as it does at -2, then this is a minimum. Okay? Let's see. At 0, it changes from positive to negative, so that's a maximum. And then at 2, it changes from negative to positive, which is another minimum. Now you could do it that way, or I like to draw, right? So let's see. This is minus, so it's decreasing, right? But then at negative 2, it turns or changes into a plus. So I'm increasing. So this right here looks like a U, which looks like a minimum to me. So this is a minimum. All right, for 0, I'll do that in blue. It's positive, right? But then at 0, it turns negative, so it goes down. So this is an upside down U. I don't know, an N if you want to call it. So this is a maximum. It looks like a high peak, whereas the minimum looks like a valley, right? So just valleys and peaks, valleys and peaks. For 2, see for the left of 2, it's decreasing, but then to the right of 2, the function starts to increase. So this is another minimum. So what we did now was we used the first derivative to figure out where the relative extrema of this function are located. This time around, I'm going to go ahead and write the locations of the minimum and the minimums and the maximum by using points. It'll always change depending on what they're asking. So there's a minimum at negative 2, and when I plug in negative 2 to the original equation, I get 0. And positive 2, when I plug in positive 2, I get a 0 as well. And there's a maximum at, let's see, it was x equals 0. When we plug in 0, you actually end up getting this funky number, the cubed root of 16. And there you go. We're using the first derivative test to figure out where there's mins and maxes. All right, example 4, same old, but now a little bit of trigonometry and the unit circle. Find the relative extrema of f of x in the interval from 0 to 2 pi. Okay, so derive. So let's see, the derivative of 1/2 x is 1/2. The derivative of negative sine x would be negative cosine x, right? Or minus the derivative of sine x, which is just cosine x. I need to set this equal to 0. So I end up with negative cosine x equals negative 1/2. The negatives should cancel out, right? So I'll just make them little pluses. And cosine x. I need x. I need to figure out what x is. So this is going to be x equals the cosine inverse of 1/2. So what this means is I need to figure out every angle where the x-coordinate is positive 1/2. So I'm going to doodle up a sign chart real quick. I'm sorry, I didn't mean sign chart. Unit circle. Okay, so I doodled my sign chart. And first off, I need to think of where is there a angle that my x-coordinate is 1/2. And hopefully you know this by now. It is 60 degrees, right? So this is 60 degrees. But we work with radians, so it's pi over 3. Okay, so then I'm going to use that to help me figure out what the other ones are. So pi over 3 is basically saying 1/3. So if I go from pi over 3, if I go over another third, so over here, right, this is another 60 degrees, I have now 2/3. So this is 2/3, or 2 pi over 3. So then from there, right, you should know that this straight line is 180. So 60 and 60. So another pi over 3, that's 3/3. And then another pi over 3, that's 4/3. So this is 4/3, or 4 pi over 3. And then another pi over 3 would be from here to here. So now it's 5 pi over 3. Now these are all the locations where my coordinate, my x-coordinate, is a 1/2, but it could be positive or negative. So my answer, or the one I'm looking for, my angle has to make the x-coordinate positive. All right, so let's see. That's not what I meant to hit. Okay, so in the first quadrant, x is positive. In the second quadrant, x is negative. In the third quadrant, x is negative. In the fourth quadrant, x is positive. So my answers are pi over 3 and 5 pi over 3. So x can equal pi over 3 or 5 pi over 3. And these are my critical values. All right, so they are both between 0 and 2 pi, so no problems there. So I'm going to use my critical values to make a sign chart. All right, so there's my sign chart, pi over 3 and 5 pi over 3. Now pi over 3, I need a number less than it, right? So I'm going to use pi over 4. Or sorry, yeah, that's right, pi over 4. So that's pi over 4. Because remember, pi over 3 is 60 degrees. Pi over 4 is 45 degrees. So that should be good enough. I need a number between pi over 3 and 5 pi over 3. So look at the unit circle. You can pick from any of these angles up to right there. So I'm going to pick the friendliest one, which is pi. Oh, there you go, pi. And then I need one that's after 5 pi over 3. Now 5 pi over 3, let's see, 60 plus 60 plus 60 plus 60 plus 60, right? 5 times 60? So that's 300 degrees, if you can remember that. So 300 degrees. I need something a little bigger than 300 degrees. Since we picked pi over 4, which is 45 degrees, let's go with 360, take away 45, right? So 360, take away 45, that's 315, and 315 is definitely bigger than 300. So we're going to go with 315. Now you're probably thinking, okay, oh my god, what's 315? Well, if this is 2 pi, and I'm basically just subtracting 45 degrees, which is pi over 4, right? So if I'm subtracting a fourth out of 2 pi, I have 7/4 left. All right, so those are my 3 values. Now I need to figure out if when I plug them in, I'm going to get pluses or minuses. All right, before I do that, in the top, in the purple, when I said make a note, these are actually values that you should learn and know what their decimal versions are by memory for parts of the test where you don't have access to a calculator. Square root of 2 is 1.414. Square root of 3 is 1.732. Of course, these are just rounded. Square root of 2 divided by 2 is 0.707, and square root of 3 divided by 2 is 0.866. So those are kind of numbers that you should get used to because they come about so often, and they make it easier on you. So when I plug in pi over 4 into my first derivative, because this is the first derivative test, when I plug in pi over 4, what I get is negative 0.207. And that's rounded, of course. So I get a negative number. When I plug in pi, I get a positive number. And when I plug in 7 pi over 4, I get another negative number. So this is a good indicator, right, to help me. Oh, we're like totally decreasing for the first part, but then it changes to increasing. So here I have a minimum, right? And then we're totally increasing to the left of 5 pi over 3, and then decreasing. So here I have my maximum. And this time we're just going to write the x value. So maximum at x equals 5 pi over 3, and then minimum at x equals pi over 3. And there you go. Next. All right, here we're sketching graphs. So this is just the beginning. I think 2 classes from now, we'll be sketching graphs together in class and go more in depth in it. But example 5, sketch a graph of the derivative of f. So, in case you can't see it, this is f. It has a little f right next to it. What we're going to do is we are going to sketch f prime. Now, is it going to be accurate? No. It's not going to be totally accurate. And all of our sketches can differ some, but there are certain criteria that it must meet. So I'm going to use the original function to try to figure out what the derivative looks like. So start off. The most important thing to start off is with the critical values, or in other words, figure out where the mins and the maxes are from looking at the graph. So here I have a min, and here I have a min. So let's see, min at x equals, and if you haven't noticed, this graph is the intervals, or the, what is it, the scale is by 2's. So this is a -2, and then this is a +2. And see, to me, it kind of looks like it's in the middle. Might not be perfect. I'm not asking for perfection here. This is a sketch. So we're going to go with that. These numbers are at -1 and +1, which makes it easier for us. Okay, so minimum. Now the maximum. Right, so the maximum here, or at least the relative maximum, is at 0. So max at x equals 0. So what you do, well, first of all, set up the graph. So hold on. Okay, so that's what I meant by set up. Do the axes, and each box is going to be 1 unit. I'm not trying to complicate this. So, since this is my min and my max, or my mins and my maxes, or whatever, this is where my derivative, f prime, is going to equal 0. This is where my slopes are going to be 0, so my derivative is going to be 0. So at these locations, my y values are all going to be 0. So I have 3 points. I have -1, 0, right here, +1, 0, and then 0, 0. So I just graphed those 3 right onto my derivative. All right, now, just like increasing and decreasing, just like the derivative can help me determine where the function is increasing or decreasing, the original function can help me determine where my f prime is. We're just going backwards. So this function f is decreasing to the left of -1. Okay, so to the left of -1, this function is decreasing. So that means on my f prime to the left of -1, so let me split these up. To the left of -1, this function is not going to be decreasing. Decreasing goes with negative. All right. So back to the original function. So between -1 and 0, this function is increasing. So let me split that up. So between -1 and 0, so right here, this function is increasing, and we use pluses to denote increasing when it comes to the derivative. Okay, so from 0 to 1, my function is decreasing, right? So I'm right here right now. This function is decreasing from 0 to 1. So I come to my derivative, and from 0 to 1, I'm going to denote that as a negative. Right? So I have a negative, a positive, and a negative. All right, last interval. From 1 all the way to what do you call it? Positive infinity or 2. If the function, if you wanted to say that that's ending at 2, go right ahead. I'm not sure. You know, for all I know, it's continuing on. No big deal. But to the right of 1, my function's increasing. So this over here is going to be a big fat plus. All right. Now, what do the minuses and the plus mean? Or the pluses. So, minus is actually f prime is less than 0. And that means below the x-axis. This part of the graph is below the x-axis. It's negative. It's below the next x-axis. And then a plus means that my derivative is greater than 0, which means that the actual graph is above the x-axis. And like I said, this is not going to be perfect. It is a sketch because I don't really know what the real y values are. But your graph should look something like this. Okay, so, you know what, let me highlight these. Okay, so I divided up these sections, right? Everything that's highlighted in green needs to be below the x-axis. Where exactly doesn't matter. This is a sketch, but it has to be below the x-axis. Everything that's highlighted in blue, in those sections, whatever function you, or whatever graph shape you decide to take, it has to be above the x-axis because it's positive. And then again for the green, negative below the x-axis, and then again for the last piece, which is positive, it needs to be back up. So here's an idea of what this should look like. So for the green section, it has to be below. So let's say I decide that this function looks like this. It's below the x-axis. I can do that. So now it has to be above, right? But only for that little section. So here you go. It's above. And then for the next section, it has to be below, but only for that little green section. So there we go, below. Wow, that curve is horrible. Let me do that again. So below, and then again, for the blue, it has to be strictly just above. So there you go. There is a rough sketch of what the derivative of this function looks like. Okay? And that's how you do that. It's really not that bad. We'll do it in class together. We actually have an activity 2 classes from now. All right, example 6. Use the graph of f prime to estimate the intervals on which the function f is increasing, decreasing, and to estimate where f has local extreme values. So this is the derivative. Okay, this is f prime. I'm going to use it to help me figure out the original function. So I'm going to write some stuff down. All right, so this is basically what we're doing. And if I were you, I would write this stuff down. So this is my derivative, right? And whenever my derivative, f prime, is above the x-axis, so for whatever parts of this graph are above the x-axis, automatically those sections, those intervals, are where the original function f is increasing. Whenever f prime is below the x-axis, this is where the original function is decreasing. So if you split this up into increase, or above, below, right? So right here, which we're going to say is -3, right here, and I'm just going to draw a dotted line. Okay, it's negative. It's below the x-axis, right? So my function is decreasing, okay, from -infinity to -3. So it's decreasing. From -3, and from what I can tell, all the way, and we're going to roughly estimate this, right, because it looks like it's 5, but to right here, let me break this up, to right there, in the middle section, this entire graph is above. So this is all going to be plus. So whenever f prime is plus, f is increasing. And then from 5 onward, right to the right, that piece of the function is below the x-axis. So this is again going to be negative. And whenever f prime is negative, f is decreasing. So what you would write is, your answers here would be everything in red. F is increasing, right? So the only section, it was in the middle. So f is increasing from, and we'll do closed intervals here. You'll see a lot of books do things very differently. Closed and open interval are up for debate. So I'll show you how to do it both ways, whatever. F is increasing from -3 all the way to 5. Okay? Now the next part of the answer, F is decreasing. So there were two sections, on the left and all the way on the right. So F is decreasing from -infinity. That's going to be open because infinity and negative infinity are always open intervals. -infinity to -3. We'll close the -3 bracket. And so let's see, the other section that was negative was from 5 to positive infinity. That's where this function is decreasing. Now this should help me figure out where my mins and my maxes are. So let's see. I'm right here and right here. These are my critical values, basically, right? Because they are zeros, if you see. And you're like, oh my god, but there's like a critical value right here at 1. And you're right. But to the left of 1 and to the right of 1, this function is positive. So that is not a min or a max. And I will take it into consideration just to show you. Right? Okay, so I use my negatives and my pluses. Let's see. Let's bring this down. So negative. This is negative. And I had a plus up here. This is positive. So either side anyway. So whatever. Positive, positive. So I made a little makeshift sign chart, right? So let's see. This is going down, but then coming up. That's a minimum. For number, or not number 1, for 1, this is going up, but then coming down. So this is a maximum. And for, oh, why do I think those are 1s? They're not 1s. I'm sorry. I draw dotted lines and I think they're 1s. This is -3, and this is +5. The block one in the middle, that's definitely a 1. And like I said, that one doesn't count because it's positive on both sides. So it'd just be increasing, increasing. But there are my mins and my maxes. So minimum at x equals -3 and maximum at x equals 5. And if you needed points, all you would have to do is plug it into an equation. But here, there's no equation to plug in, so no points necessary. And that's that. All right. Do your homework, please.